This video is for Lab 12, Chapter 39 of the Applied Analog Electronics textbook. In particular, we'll be looking at impedance spectroscopy for stainless steel electrodes. Let's take a look first at the physical setup. What I've got is a beaker, or drinking glass, with the stainless steel electrodes in it. The stainless steel electrodes, there are two of them. There's a little plastic spacer in there, and below the spacer I have the solution that I'm going to be testing. Now, because I was doing this at home without access to normal lab equipment, what I did is I made up a 1-liter bottle with 35 grams of sea salt, just from the grocery store. So 35 grams per liter is approximately the same concentration as seawater. I could have gone down to the beach and gotten some seawater, but it was easier just to make this at home. Okay, so 35 grams per liter is concentration roughly of what seawater is going to be. It's not extremely concentrated salt water. Normally when we do this in the lab, we use 4 different concentrations, 1 molar, 10th molar, 20 millimolar, and 5 millimolar. To get down to the lower concentrations, you have to use distilled water because tap water, at least in Santa Cruz, is got a higher concentration of salts than the 5 millimolar solution would have. So what you're going to want to do in the, for your home lab is to make up a concentrated salt solution with some roughly known concentration based on having measured the salt and the water that you're putting in, and then do serial dilutions using distilled water to get a number of different solutions of relative known concentration. Even if you're not absolutely certain of the absolute concentration, you'll know that, for instance, your second solution is 1/10 the concentration of your first solution, and so on. I'm just going to do the demo here with one concentration. The technique is exactly the same with other salt solutions. You go through the same steps for each one, and just do it repeatedly in order to get a good set of data. Alright, so the one thing to notice here is that the water level here is in the middle of that plastic spacer. You want to be wetting the electrodes below the spacer, but not above the spacer. And that way you can get consistently the same length of electrode being wetted. If you were trying to rely just on the depth of the liquid and you had the metal wires sitting there and there separately, it would be difficult to get it consistently to the same depth. The plastic spacer gives you a little bit of flexibility there in exactly how much the liquid level is. The thickness of the plastic is sort of your tolerance for how much you fill the liquid. Okay, up at the top here you can see I've got two alligator clips on the electrodes, and they are running off to the Analog Discovery 2. Here I'm using the impedance analyzer board, which you're not going to have, but you can get exactly the same effect by going to a breadboard and having a resistor in series with the device you're testing here, the electrodes. So it's exactly the same as what you did for the loudspeaker lab. I won't bother showing you the breadboard for that. But, let's go and look now at what we do with this thing in waveforms. Okay, so first thing is we're going to want to use the impedance analyzer, and I never like the way they've set it up to show you the real and imaginary parts of the impedance. I much prefer having it in terms of the magnitude of the impedance and the phase. And we'll be doing all our fitting with the magnitude of impedance, so this works just fine for us. And because I'm using the adapter board, I'll select the adapter board. You should select whatever wiring setup is appropriate for what you're doing. And before I do compensation or anything, I'm just going to do a quick run through this thing. Here it's the default setting 1 kilohertz to 1 megahertz. That doesn't take very long to run, and it'll give me an idea what size resistances I'm dealing with. And this is looking like it's around 10 to 30 ohms in the concentration of salt that I've got right there. If you've got a higher concentration of salt, you may have much lower resistance. If you've got a low concentration of salt, you might have a much higher resistance. So this is going to depend. This is going to vary a lot depending on what you've got. So knowing that it's around 20 or 30 ohms, I don't think a 1 kilo ohm sense resistor is probably going to be about right. And I'll probably want to run to much lower frequencies than 1 kilohertz, so this is going to go up. Maybe it'll go up to 100 ohms or so. So let's pick 100 ohms as the as the reference resistor. And again, you would have to change the resistor on your breadboard when doing this. One of the nice things about using the adapter is it uses little relays to change the resistor for you. And I will change this to, say, let's go down to 10 hertz. That won't take too long. You might want to go to an even lower frequency, and why not? I'll go all the way up to 10 megahertz. And if we just do a single run here, notice that the low frequencies, it takes a while. And so that's why I didn't go any lower than 10 hertz here, is that because it takes many cycles at the low frequencies, it takes a really long time to make each measurement. And then it speeds up as you get to the higher frequencies because it takes less time to get through enough cycles. Okay, now this curve that I've done here has got no short circuit or open circuit compensation, and so I don't regard any of this data as correct. It's just giving me an idea that, okay, the 100 ohm sense resistor was a reasonable choice for this concentration in these electrodes. Okay, now I've got to do some compensation. The compensation menu here, I can do open compensation first or short compensation first. It doesn't really matter. Let's start with the open compensation. So to do that, it's going to remind me that I have to leave the terminals open. So let's take a look at how I do that. I don't want to change the position of the wires much, because what I'm trying to compensate for is the inductance and capacitance of the wires, and if I move them around, I'm changing their inductance and capacitance. So I'm going to try and move this, to get an open circuit here, I'm going to move this pretty much as little as possible, just clipping it to the side of the glass there. And now I've got open circuit. And we can see that we're seeing stuff up in the tens and hundreds of mega ohms, and compared to a 100 ohm resistor, basically that means we're seeing just noise across the 100 ohm resistor. And as we get to higher frequencies and the impedance goes down, which is what we expect if it's mainly capacitive impedance, which is what we expect usually for an open circuit, then we can see we're no longer getting just noise. Okay, one thing you can do, and that's actually somewhat interesting to do, is you can export this. And I can export this as the open compensation, and here this was the 35 gram per liter stainless steel. And I'm saving everything from the impedance analyzer. That gives you frequency, phase, and magnitude. Those are the values I want. I can save this. And this was open stainless steel 35 gram. Okay, now I'm going to want to do the short circuits compensation. So I'll perform the short compensation. And, okay, now I'm going to want to hook these things up again, and I'll just connect both electrodes, both the alligator clips, to the same electrode. And going through doing the compensation here. Now we can see that at low frequencies we've got 300 milliohms. So that's probably the resistance of the wires. There may be also some resistance from the relays and stuff on the impedance analyzer board. And it starts going up with high frequencies here, and that's what we expect because we had a loop of wires there. My wires coming over to here are a couple feet long. So there's quite a bit of inductance, and so we see inductance increasing impedance with frequency. And we saw something like that on the original measurements when we did it without the compensation, and we may have been just been measuring our test set up there and not the electrodes themselves. So now let's enable both these compensations and go back to here and set this up. And I'm using the alligator clips here partially to keep the electrodes vertical in the jar there so that I'm not getting liquid slopping over the top. And if you're getting a lot of problems, if you get the top surface really wet and you want to dry it off with a cloth or something, that might be a useful way to make sure your measurements are a bit more repeatable. Okay, let's go back to here. Oh, I never exported the short circuit information. I should do that. Okay, and now I'll do a single run to get the measurement. If you've got a lot of time, you can often improve the measurements a little bit by averaging multiple measurements, and there's an averaging menu up there that lets you do that. Okay, our measurements are looking at the low frequency end. They're looking pretty much like they did before, starting about 300 ohms. But notice now we don't see much of that ticking up there at above 100 kilohertz. It doesn't start ticking up until we get close to 10 megahertz. And that means we've got much less inductance because we're compensating for the inductance of the wiring. We probably still have a little bit of inductance left because those two electrodes, we have the connections at the top and then there's a loop coming down through the solution. So there's still some inductance in our electrode setup. But it's much, much smaller than the 2-foot long wires that I had before. And we can export this data. And this is the measurement. Okay, so that's really all there is to doing these measurements. Picking a resistor, getting the short circuit and open circuit compensation done, making sure that you enable those compensations, because it doesn't do any good to make the to measure the open circuit or short circuit behavior if you don't then enable it to make sure that the software subtracts off the results of that. Once you've got the data and you've exported it, the next step is to fit models to it. And I'm not going to do that for you. It's very similar to the model fitting you've done before. Your main choice is to figure out what model you want to use. What have you got here? It looks like at low frequencies we've got something that's either a capacitor or a capacitor-like thing. Is this going down by a factor of 10 in a decade? It doesn't look like it because it's only going from about 70 ohms here to about 20 ohms in a decade. That's not a factor of 10. So this doesn't look like a pure capacitor. We could use our nonlinear impedance with the appropriate slope to model this part of the curve, and then we've got that in parallel, in series, you figure it out, with something that looks pretty constant. That's a resistor. I wouldn't bother trying to model this little bit here above 5 megahertz. You could if you wanted to, but it's probably not an interesting property of the electrodes since we're most likely not going to be using them anywhere near that frequency. So it's a question, do you want to model this small amount of inductance here or ignore it? Your choice. If you do ignore it though, don't try and fit this part of the data. Just fit out to the part that's still modelable by the simpler model. So that looks like, if you look at the phase plot, it looks like you can model out to about here fairly well with, so that's what, 2 megahertz on my data, with just a resistor and capacitor-like element. If you want to go much beyond the 2 megahertz, then you might want to model a little bit of the inductance. Okay, you'll want to do the same thing with different solutions and plot the measured impedances for your different solutions with the stainless steel electrodes all on the same plot, so that you can say, oh, what is the effect of changing the concentration of the electrolyte? Does it change the behavior? Which parts of the behavior does it change? Which parts does it not change? And trying to understand what's going on by looking at the data. And I'm not going to do that for you, but that's the goal of your lab, is to basically repeat this measurement for 4 different concentrations that you know about. You can add another one like tap water that you don't know about, but 4 that where you know the relationship between the concentrations. And do make up your multiple solutions using distilled water, because otherwise the low concentrations will be really not proportional. Tap water is nowhere near free of electrolytes. Okay, that's about it for this video.